This diagram shows exactly where our algorithm sits among the 50 algorithms every programmer should know. Under the association rules category, we have FP growth. The goal here is market basket analysis, identifying items that frequently occur together, like products bought in the same retail transaction. To understand why FP growth was such a breakthrough, we have to look at how the previous standard, Apriori, handled data. Apriori operates on a generate and test philosophy. It makes a guess about which item combinations might be frequent, then scans the entire database to see if those guesses were correct. This lattice diagram illustrates Apriori's core weakness. It generates candidates level by level, single items, pairs, then triplets, rescanning the database each time. Look at the bottom. The combinations explode. Finding a 100-item pattern means generating 2 to the power of 100 candidate sets. On dense datasets, this method mathematically collapses. The solution isn't to compute faster. It requires a structural approach, one that stops guessing possibilities entirely, and instead changes how the information is physically organized. FP growth abandons candidate generation. Instead, it compresses the entire database into a shared prefix tree using exactly 2 database scans. This shows how that first scan works. Using a dataset of cricket gear, the algorithm tallies the frequency of every item. Anything that falls below a minimum support threshold, like this single instance of balls seen here, is completely dropped from the list. The surviving items are sorted by descending frequency into an F list. By reordering every transaction to follow this sequence, the algorithm ensures that the most common items will sit closest to the root of the tree we're about to build. During the second scan, the algorithm takes each of those reordered transactions and inserts it into the tree. Starting from a null root, it maps each item as a downward path. This is where the compression happens. Notice the helmets node with a count of 3. When different transactions share a prefix, the algorithm reuses the existing nodes and simply increments their count. It only branches off when the items in the transaction diverge. By prioritizing frequency and sharing roots, the FP tree becomes a compact, lossless summary of the original dataset. We've mapped every relevant relationship without generating a single hypothetical candidate. Construction is only the first half of the process. To actually pull out the frequent item sets, the algorithm reads the tree from the bottom up. This diagram breaks down the divide and conquer extraction method. We pick the least frequent item, wickets, and follow a side list called a header table to find every prefix path in the tree that ends at wickets. This collection is called a conditional pattern base. From that base, we build a smaller, conditional FP tree. We prune it by our support threshold and repeat the process recursively until only frequent item sets remain. This Venn diagram shows the end result of all that recursive math. That pink intersection represents the specific overlapping transactions where 2 items appear together. FP growth achieves this entire mapping process without ever needing to go back and rescan the original raw database during the mining phase. By reorganizing the data into a shared prefix structure, the algorithm avoids the combinatorial explosion that stops other methods. To see exactly how this tree is constructed in Python, let's open the notebook.
We've seen how FP growth compresses a database into a prefix tree in theory. Now we're going to translate that structure directly into functional Python code, so you can see exactly how these paths are created and shared under the hood. Everything starts with the node class. When a node is created, it needs an item name, and we initialize its count at exactly 1. From there, the tree needs a way to branch downward. We handle that by giving each node a children's dictionary, which maps to the next items in the transaction. But the vertical branches aren't enough. We also need a horizontal connection for the header table side list. That's what the link variable is for. By combining a vertical tree with a horizontal linked list, we've created a dual structure. This exact architecture is the absolute prerequisite for making the algorithm run efficiently. Moving beyond the single node, we need to assemble the full structure. The entire tree building process takes exactly 2 passes over the data. We begin with the build tree function and the first loop. We return to the code for the second pass.
Here, the function loops through those newly reordered, frequent item-only transactions. As we step through a transaction item by item, the program faces a decision. How does it know whether to reuse an existing branch or build a new one? We handle that with a simple condition. If the next item in the transaction is already registered as a child, we skip creation entirely and just increment that existing node's count by 1. But if the path diverges from the established tree, the else block triggers. This is the only time a fresh node is instantiated. Once that new node is created, we use a splicing mechanic. The new node is connected to the header table's side list, guaranteeing the mining phase can find it later. These specific conditional lines are the actual compression mechanism in code. They prove that the tree maps the entire database directly without ever generating or testing a single candidate item set. Finally, the build tree function outputs a fully linked root and header table. That output becomes the foundation for the entirely separate mining phase. In production environments, data engineers rarely write this out from scratch. Libraries like Spark MLlib wrap this exact complex recursion into a single execution command. If you want to inspect the raw Python implementation and step through the recursion yourself, the code is available in the official course repository. That same structure becomes a massive memory liability. We're talking about FP growth. It's the canonical engine behind market basket analysis, the math that populates frequently bought together prompts and tells mega retailers exactly how to optimize their store layouts. It scales directly into digital infrastructure, mining millions of web click streams to map out and predict user navigation paths. You'll also find it deployed in advanced scientific and security domains, hunting for recurring genetic motifs in bioinformatics, or scanning server logs to find the exact combination of events that signal a cybersecurity breach. Across all these different deployments, the mission is identical: mining massive walls of raw, unlabeled transaction data to extract the hidden, repeating patterns buried inside, ignoring the original database entirely. When data has heavy overlap, this tree stays incredibly compact, resulting in processing speeds about an order of magnitude faster than legacy methods. That architectural efficiency translates directly into modern production reality. In massive enterprise deployments, this speed is exactly why it ships at scale within Apache Spark's MLlib as FP growth. It also acts as the primary association engine inside Python data science ecosystems, powering libraries like MLXtend. Modern systems rely on it to handle massive transaction volumes, where older algorithms would immediately crash. Assuming your data possesses the structural overlap it needs, FP growth is the undisputed industry standard. But that speed relies entirely on a structural bet. We need to look at what happens when that bet fails. The hazard here is sparse or wide data. This occurs when transactions contain hundreds of distinct items, but share almost zero overlap with each other. Without shared prefixes, the tree cannot compress. It balloons uncontrollably, turning an elegant data structure into a fatal memory liability. There is also an absolute mathematical limit. If you set your support threshold extremely low, the total number of valid patterns naturally explodes into an exponentially massive list. When that happens, no algorithm on Earth can mine it efficiently. That explosion is an inherent property of the mathematical answer, not a flaw in the miner. FP growth makes a clear trade. It sacrifices candidate generation for intense memory pressure, and on unstructured data, that trade goes bankrupt. You also have to account for its analytical blind spots. The algorithm finds strict co-occurrence, ignoring both the quantity of items bought and the exact order they were purchased in. From a systems perspective, an FP tree is notoriously difficult to parallelize or incrementally update compared to a simple flat database scan. And crucially, a frequent pair discovered by this math is merely a correlation demanding further investigation. It is never a proven cause. Even so, the enduring lesson holds true. Implementing the right data structure can completely erase an entire class of computational work. By compressing a database into a tree, FP growth deletes the need to guess candidates, extracting every hidden pattern in exactly 2 passes. This is just one of 50 algorithms we've deconstructed from end to end. It's based on the book 50 Algorithms Every Programmer Should Know by Imran Ahmad. Head over to neuralsca for the code, the underlying stories, and the complete breakdown of all 50 algorithms.